So I will start. So when others join, we can join them. Okay. Is it okay? Hello.
Yes, sir.
Is it okay if I start now?
I think
There is only three.
one is waiting. Yeah.
Are
Cool.
there-
Dhyan, Akhil, one is waiting.
So lecture number 5. Before I start that part, I will recap last lecture. Last time what we discussed. This is a ideal specimen stress cycle SN diagram. So we discussed this one, and non-ideal specimen without stress tracer. And last time we discussed when we introduced the stress tracer to the element, what happened to the stress and how we can calculate the stress and other things. So this is the stress profile, how it can be uh, vary with around the stress razor. So so this is the kind of simulations. So I'm briefly explain. Okay, and this is the von Mises analysis around the I mean across the stress razor and the element cross sections. You can see the stress is very high, and I told you I will discuss this with this equation and other things later, because we will discuss thick wall cylinder sessions. I will discuss this equation furthermore, how we can derive this equation and other things. But when we introduce a small hole concentric hole into this solid disk, so that stress will be 2 times rather than in here. So you can see, so with this equation this is 2 times, and so this is the one quadrant of this circle. So how stress is in the y direction and x direction stresses are vary. So this is the y direction, this is x direction, so stress variations we already discussed this thing. And when different geometry, if the stress tracer, if it doesn't have, doesn't have only circle only. So if it is a different shape, so we can get the general shape as ellipse. So there is a diameters. So if we change a b dimensions, it will change the geometry of the that stress tracer. So this is the equation for the kt, stress conservation factor. Kt is the stress conservation factor. So a and b is, if it is equal, kt value will be 3. So we already derived that equation also. And yeah, so this is according to geometry how it can be vary. a AB ratio, if it is reached to 0, that means there is no any uh, I mean it is parallel to the loading direction, so it is not too much effect then. So okay, it is reached to 1. And if it is yeah, this is the way of KT, I mean stress ratio if it is parallel to loading direction, so stress is not too much arise. And then AB ratio, if it is infinite, that means the A value is larger. That means you can see this is flow direction, so that will be something like that. So that then stress will be very high. So KT value also will be high. So this is the things you can see. We already discussed these things, and you can see the different analysis. I mean, this is one business analysis. This is yeah, shear stress and other things. So already I discussed these things. I'm not going to go through in detail everything. And we can find out the KT value using this kind of graph at the exam. And if you want to find out the according to geometry and loading condition, so you can find out the KT value according to a proper diagram. You need to select the proper the graph, then you can find out the KT value according to the ratio of DH and DB, like that. So you can see this is thick plate, the holes penetrate to the other side. So if you have this kind of stress razor, you need to use this kind of graph with the bending. And if it is axial load, you need to use this kind of graph like that. And so this is when we change the stress razor, radius. So if it is circle, it's size. When we change, how stress vary. Simulations is explained in here. And around the stress razor area, there is stress profile you can see. So due to that, you can remove the material if you want, because this is unnecessary material. But you can use that material, that area, to strengthen the element. So you can use this kind of additional stress razors to distribute the stress. So it will be dilute stress around this area, and then maximum stress will be lower than here. In here, stresses will be lower than. So we already discussed these things. And this is the poor design. This is the good design, you can see. So rather than put in one hole, you can put two another holes, the overlapping hole near to the that particular hole. So we can use a pillar or something like that. And you can use even though non-ideal specimens 10 to the power 3 fatigue strength is not reduced, in here with the stress razor 10 to the power 3 cycle strength also reduced. So we need to find out the K, that Kf dash, Kf prime value at the 10 to the power 3 cycle. So you can use this graph to find out the Kf dash, and if you want to find out the Kf, you can use this diagram. So using this diagram, you can find out the Kf. So we can find out the Kt, Q, Cs, normally service factor we will find out. And you can find out Kf. Using that Kf value and ultimate tensile strength, you can find the Kf dash. So that's the way. So if you change the pillar radius, you can see how vary the maximum stress around the stress razor. You can see. So there is a critical size. You can't put any size for the pillar. So you need to select the optimum size. And this is the new curve for the SN curve with the stress razor for non-ideal specimen. You can see at 10 to the power 3 cycle also it is reduced, and 10 to the power 6 cycle, that means induced limit for this tail, so it is also going to reduce. So when we divide by Kf, in here 10 to the power 6 cycle, when you calculate the strength, you need to divide by Kf. 10 to the power 3 cycle, you can't divide by Kf, you need to divide by Kf prime. So these are the parameters, variables govern the KT and CS and Q. So all those things govern the Kf value. So specimen geometry, loading type, it will govern the KT, strength and surface finish, radius and loading type and strength govern the Q value. So I already explained how we can, if you don't remember these parameters, how we can get from these parameters from the graph. Last time we discussed this. So today we will discuss about the additional thing. So until today, we only use only one stress cycle. Stress pattern. One stress pattern. Okay. Before I start this new session, so do you have any questions for the last few sessions? If you have any question, you can ask. Tihan or someone else. If you have any question, you can ask. Don't you have any questions? Okay. So I couldn't hear if you switch. If you mute your mic, I couldn't hear anything. Okay. Okay. So you can see in here. This is very complex stress pattern. So with the time, the loading even though this is loading, stress also vary with the same pattern. So stress cycles are different stress cycle you can see. So the single stress pattern, it will be something like this. Okay, I will draw in here. So if you use a single stress cycle, so if you repeat this stress cycle, alternative stress cycle, so we can calculate now everything with this kind of stress cycle. But if we apply this kind of nature, you can see in here, it's very complex. So how we can calculate the strength and other things, we will discuss in this lesson. So, but there is a different range of stress cycles. So we need to do we need to use some theory. So we call that theory is minus rule. Okay? So what happened if you apply? I will go to next slide and I will. So I draw in here. You can see assume this is S1. Okay, maximum stress is S1. Then this is the stress value we are going to apply. Okay. So it is, if it is higher than the endurance limit, if it is higher than the endurance limit, it will damage the specimen. Okay. But if it is lower than this endurance limit, okay, assume this is Sn dash. So if it is, okay, as a value, I will put as 100. So if it is lower than 100, Sn endurance limit is 100 megapascal. If it is lower than, we are going to apply the lower value than 100. So it will not damage the specimen because we can apply that stress range until infinite lifetime. So without damage. But if you apply higher than 100, so just assume 100. So if we apply higher than 100 stress range, so you can't apply that particular stress range until infinite fatigue lifetime. So it has a limitation. So you can find out the equation. You already know how to find out the equation of this curve. So if you can find out the equation, you can find out the S coordinate, that means number of cycles. So if we apply this higher stress, or we call it over stress actually. So if it is over stress, so with that over stress, how many number of cycle you can apply with that much of stress. But if you are not going to apply 10 to the power 5 cycles with this range, so we will only apply 5 or 10 number of cycle with this range. So even though we apply 10 cycle with this stress range, it will damage the specimen. So that is the meaning of the cumulative damage. So we will apply different type of ranges. So we need to calculate the relevant stress range, how much damage the specimen, and we will get the summation of all the damage and calculate the final strength. So that's how we can do the equation with this theory. So do you have any questions? Did you understand what I'm explaining? I won't answer, otherwise I don't know. At least one person.
Yes, sir. Thank you.
So lifetime will be reduced. If you apply the higher stress, lifetime will be reduced. Okay. So yeah, as I told you, so if we apply one cycle with this stress range, it will consume 1 upon 10 to the power 5 lifetime from this specimen. Okay. So, but it is not affect below the Sn prime range. If you apply, it is not affect to the specimen lifetime. It will not reduce the lifetime. Okay. So when we do the calculation with the minor rule, this is the minor rule. The linear cumulative damage rule assumes that total life of the part can be estimated by simply adding up percentage life consumed by each overstressing cycle. So you know what is overstressing cycle now. So if you need to get the ratio between the if you apply that particular stress range until breaking, so you know what is the number of cycle you can calculate using the SN curve equation. So that is the capital N. And simple N means how many cycle you are going to apply on this specimen with this stress range. So that is the damage, the ratio you can see in here. So if you apply one cycle, so this is simple N. So this is the total number of cycle you are going to apply to break with this stress range. So 10 to the power 5 cycle. So this ratio, the summation of ratio should be equal 1 if it is break. Okay. So we can simply say this way. So J means the 1, 2, 3, 4, 5, 6 until K. That is mean the different type of stress ranges. Okay. So K type of stress ranges are there. So J to K. Okay. J can be 1 to K. That's meaning. So are we clear about that? So this is the minor rule actually. So how we can see how we can do with the question. This how we can apply this rule with the equations later. But did you understand the theory?
Excuse me, sir.
Yeah.
So what is J?
J just you can put as a I. If you want to put as a, doesn't matter. Just
Okay.
for a general type.
Okay.
So if it is
Okay.
one first type of stress range, it is 1. Second type of stress range, 2. That's the way.
Okay.
So this
Okay.
is simplification.
Okay.
Same thing. When we note down like this, it is very difficult to write down. So this is very easy to write down. Okay.
Yeah.
So generalize. Okay. So this is minor rule. So with this example, let's see how we can use that minor rule. Okay. You can see there is a x-axis, y-axis is load. This is stress. Sorry, this is number of cycle, not load. Number of cycle. This is stress. So you can see stress range. Okay, 100 to 200, and 200, 300, 300, 400, 400, 500, 500, 500 to 600. So I think you know this kind of bar chart. This is kind of bar chart. We can say histogram as well. So not bar chart, it's histogram. So you can draw the line like this, no? So you can say, so actually this is the actual stress variation. You can divide it to stress range like this. Okay. Already they did in this example. You don't want to do that. So given SN curve for particular steel and the stress duration curve for applied load, calculate the estimate life of the component in hours. So in ultimate tensile stress given, assume 10 to the power 3 cycle strength 0.85 S2. So this is not a 0.9 there, okay? 0.85 S2, and SN prime, that is an endurance limit, 0.4 S2. So how we can deal this kind of questions? Let's see. So even though this is stress range, you can't consider the whole range. You need to consider one particular value. So you need to get the mean value of this range. Okay. So it will be 150. In here 250. So you did this kind of calculation in your O level as well. So 10 to the power 3 cycle, that value is given. Okay. So this ratio is given 10 to the power 3 to that ultimate tensile stress range ratio is given. So if you know ultimate tensile stress, you can find out the 10 to the power 3 cycle strength. So 10 to the power 6 cycle in here. In here they mentioned that 3 times 10 to the power 6 cycles strength. So you can find out the 10 to the power 3 times 10 to the power 6 cycle strength SN prime using this ratio. Okay. So you hope you remember this equation we discussed last time. So with this equation, you can substitute two values in here. You can see. So they expand this equation with the logarithm. So substitute and find out the a and b. Because so why we are going to find out this Sn equation? That relationship between the strength and number of cycle. Do you have any idea? Very first thing, you need to find out the Sn curve, that the linear region equations. Do you have any idea why we are going to find out that Sn relationship? So anyone? Are you there? Tihan or someone else? Can you give me an answer? So why we are going to find out the first that the equations constant values a and b? Do you have any idea? I couldn't hear anything. If you don't know, you can tell me. Hello. Hello.
Yes, sir.
Hello. I can't hear you. Hello.
We don't know, sir.
Can you all hear me properly? Because I couldn't hear you properly.
I can hear you.
Okay. So do you know why we going to find, we are going to find out this equations a and b values? Tihan? Hello. I don't know. Did you give the answer? I don't know. So why I'm asking, because you should know why we are going to find out these equations. Otherwise, you are blindly doing the calculation. That's why. At least someone. I don't know. I couldn't hear.
Sir, not sure, sir.
Not sure. Actually, we.
Excuse me, sir.
Yeah.
To find the negative and the positive of this trend.
Negative and positive. Can you explain furthermore what is that negative and positive?
It's mean x equals minus something.
No. Actually, so if you remember when I explained here, so we have different stress range, no? With this question, you can see different stress range. We will consider the mean value 150 and 250 like that. So with this stress, we should know what is the total number of cycles to break this sample with this stress range. For that, we should know that equation. So capital N, when we are going to find the capital N, because with these questions, you can find out the N, sorry, S, that means stress value, but you can't find out the N. This N is simple N, okay? This is not a capital N. So this is given, the 150 stress range will be applied with the number, this is around 100 number of cycles. But with the 100 number of cycles, this sample will be not break. So we need to find out the actual capital N, isn't it?
Yeah.
So for that, we should know the equation. The particular element, the relationship between the S and N is not changed. Even though we change the stress range or number of cycle, the SN relations is not going to change for the material. Okay, so that's why we are going to find out the relationship between the S and N. Then if you substitute S in here, you can find out the N if you know A and B. That is capital N, total number of cycle to break with this stress. Are we clear?
Yes.
Okay, so
Yes, clear.
any doubt? I had something. Do you have any questions?
No, sir.
Okay, so so you can substitute 10 to the power 3 cycle strength and 10 to the power, that endurance limit. In here they mention endurance limit is 3 times 10 to the power 6. So you can substitute here and find out A and B. I'm not going to explain how to do the calculation with the log. So A and B you can find out like this, and this is you can substitute in here. So we can rearrange that equation because we don't want to find out the stress now. We need to find out the number of cycles. So you can subject that N and like this. So you can substitute here A and B. So this is the final equations for the relationship between the S and N. So if you know stress, you can find out the total number of cycle to break it. This is fatigue lifetime for the material. Fatigue lifetime with the relevant stress. Okay, so when you change the stress, if it is over stressing only, okay, this equation valid if it is over stressing. If you remember in here, so this region valid above endurance limit, you can see. So below endurance limit, you can't apply this equation. Okay, so this is constant, so it is infinite fatigue lifetime. Are we clear? So
Yes.
So this is the equation. So you can
Sir,
see.
so
Yeah.
Only above the endurance limit, minus law is applicable.
Sorry, can you repeat it?
We can only use minus law above the endurance limit.
Minus. Why minus?
Well, because minus law is, if it breaks, it's equal to 1, right, sir?
Minor rules. Okay.
Minus rule.
A minor rule. Okay, I heard minus something like that. Okay. Okay. So yeah, with the minor rule, you need to find out the simple N and capital N. Simple N means how many number of cycle you are going to apply with this stress, and capital N means with that stress how many number of cycle you need to apply to break this particular sample.
So above the endurance limit, below the endurance limit, you can't use minus rule.
Not the minus rule. We don't want to use minus rule because below the endurance limit, there is no point to apply the minus rule because it is not damage to the sample.
Yes, sir, understood.
Yeah. So if you apply the over stressing only, we need to apply the minor rule. Okay. You can see with this example. So this is x-axis, this is y-axis. So we can fill so like this. So you need to represent this range with the one single value. You can't use the range of the value in here. So you know that if you have in your O-level also, you find out the x and f something like that, and you will find out the fx something like that. No, in the statistics you did this one. Okay, so you need to find out the mean value of this range. So this is 150, 250 like that, and then you need to use this equation. But you can see in here 150 and 250, that n value, it's infinite. You don't want to use this equation because if you remember in these questions, ultimate tensile strength, sorry, to 650. So you can find out the endurance limit using this equation. So you need to substitute here 650. So when you substitute here 650, what is the value? this will be around 260. Yeah, it will be 260. Okay, so 260 megapascal. Below 260 megapascal, it is not overstressing. So endurance limit is 260 megapascal. Are we clear? So you can see
Yes,
here
sir.
150 and 250 below 260. So you don't want to use this equation. It is infinite. But 350, 450 and 550 is above endurance limit 260. So you need to use this equation. Just substitute 315 here. Find out the capital N value. Okay. So just substitute here 350. So you will get the value for capital N. In here they put NH, but this is assumed as a simple N. Okay, because per hour they gave this stress cycle per hour. Should remember, yeah, component in hour. That's why. So we will repeat this. They will repeat this stress cycle next hour, and like that they will repeat within hour all the until breaking point this stress pattern. So you can find out the simple in that or simple NH per hour number of cycle you are going to apply with this stress. It is 90 and 165. This value 270. Likewise, you can find out the simple N value. Then what you need to do, find out the ratio between these two. So if you apply if you got the ratio from these two, it is 0, definitely. When you divide something infinite, it's 0. So that's mean the below endurance limit, it will not affect to the lifetime. You can see. Okay. So when you get the ratio of these two, those are the values. So you need to get the summation. This is the minor rule. You need to get the summation. Are we clear?
Yes, sir.
So this is 0. The summation is 0.1197. So assume 0.12. This is 0.1. If it is 0.112, so this is from out of 1. So out of 100, it is 12%. So that particular specimen within 1 hour, 12% will be damaged. 12% damage will be happen. Okay. So how we need to find out the component lifetime? So this will happen within 1 hour. Okay. So within 1 hour, damage if it is like this, you need to divide 1 by this value. So you will get the total hour to break this specimen. Because if it is equal 1, it will break, isn't it? Are we clear? So this is the total component lifetime. So after 8.35 hours, that means 8 hours and 3.35 means around 15, not 15, 20 minutes, something like that. Which is like a 35% or something like that. No? So then it will be around 16 minutes. So 8 hours, 16 minutes, it will break with this stress range. So we will apply each hour this kind of stress pattern. So this is the component lifetime. Are we clear? That question are clear? So you understand how we can use that minor rule, no? Any questions about that example? If you have any doubt at any point, you can ask.
Excuse me, sir.
Yeah.
So what is NH? NH per hour?
That is similar to simple length. So in here, this is the number of cycle you are going to apply with this stress range. Okay. So with this stress range, you are going to apply this number of cycle. But this number of cycle they will apply within 1 hour. So in the question, if you check, you can see component in hour. The calculate the estimate life of the component in hour. So stress apply load. So they will. So if you go through the lecture note, so they will apply this stress ranges within 1 hour. Okay, they mentioned it. So I think they reduce something in here. You need to find out in hour. So they will apply this stress range within 1 hour. Okay, so this is within 1 hour stress variation. Are we clear?
Yes.
So if this variation happen in 1 hour, you need to find out. So it will repeat again and again each hour. So within 1 hour, this is the damage. This is the damage. But when you find out the within 1 hour, because this is not a simple n. Next hour, another 90 cycle will be applying here, no? Isn't it? That's why they
Yes,
mentioned
yeah.
per hour n. Are we clear?
Yeah.
The next third, then after second hour, third hour, it will be 180.
Yes.
Are we clear?
Yes.
So within 1 hour, this number of cycle will be applied with this stress. Are we clear?
Yes.
So if you have lecture note, you go through that one. There is mentioned within 1 hour this stress apply. Okay.
Okay.
So another example in here. So solutions. If you have lecture note with you, just take that lecture note. I think they didn't explain the answer in here. Okay. So you can see in here there is a shaft, part of shaft. So you can see the pilot in here. They mention estimated fatigue life of the shaft corresponding to the specific loading. So they provide the within 20 seconds. Earlier they provide within 1 hour stress variation. In here they provide us within 20 seconds stress variation. You can see. So you need to find out first. Okay, so you can see here. This is 20 KSI. 20 KSI. How many number of cycles within 20 seconds? 1, 2, 3, 4, 5. Okay, so you can count like that. This is 25. Only one. This is around 12. This is around 13, something like that. So you can count like that and get the frequency of the stress, each stress range, and then you can convert to the stress range to the megapascal. So you can't use that equation for the KSI. So convert to the megapascal. They provide us the how to translate to the KSI to megapascal. So then you can use same minor rule with this kind of table. So always use this kind of table in this kind of questions. Okay, don't do manually these things. Just get the stress range, mean value. If it is range, you need to get the mean value and get the equation for the SN equation. Then find the total number of cycle to break and the applied number of cycles you need to put in here and get the ratio and get the total. This total. Okay. This is like if you remember in your O-level you did in statistics. This is X. This is F. You will get the sigma fx, something like that. You will get the fx, then sigma fx, something like that, similar to that particular table. So they didn't explain in here how to do the calculations. So hope you can manage that. So if you have any questions, you can ask. I can open if you want. lecture note. Can you see my?
We see the PowerPoint
Yes, no?
slides, sir.
Okay. Uh, can you see now?
That's the electrified. Yeah.
Yeah. Okay. So you can see the explaining here. You can find out the SU, ultimate tensile strength. Then you can find out the values related to that. So I'm not going to explain that one. And then find out the SN equation. Okay. So you know everything up to here. So in this question, they didn't provide directly 10 to the power 6 cycle strength and 10 to the power 3 cycle strength. You need to find out. You know how to do that. So these calculations you should do. Okay. So find the K prime and then 10 to the power 3 cycle strength and substitute these equations, get the A, B values. Then you know the SN equation. Then K's I value convert to the megapascal as I told you. The number of cycle you can count. Then this is the value you need to get from the SN equation. Okay, so this is the simple length. So you need to get the ratio between these two. Get the summation. So this will apply within 20 seconds. So this is the number of cycles within 20 seconds. So you need to find out the you need to divide the 20 seconds from this number of cycle. So if you convert to the hour, you need to divide by 3600 because this is second. So you can convert, if you divide by 3600, then you will get the answer for the estimated life 32 hours. Are we clear? Did you understand?
Yes.
So if you have any question, you can ask. Okay. So I think you can deal with this strength calculation. Okay. 10 to the power 3 cycle strength and 10 to the power 6 cycle strength. This is SM prime. I mean endurance limit. So these calculations you should do. So I will move to the slide then. Can you see slide now? Hello?
Yes, sir.
Okay. Yeah. So now you know how, rather than applying one single stress throughout the time, if we can change the different with the time, we can change the stress range as well. But all of these things are alternative stresses. Okay, alternative stresses plus. So if we apply plus tensile load, same time we will apply the minus compressive load. That is the meaning of fully reverse bending. If you remember, fully reverse bending means I will draw in here. So if we apply this kind of stress, this is called fully reverse. This is positive value. Assume this is plus 50. This is plus minus 50. So completely reverse compressive load. Even if you consider this is tensile direction. So tensile, if you apply the tensile load, same time within few seconds, the same point will be under compression. Okay. So this is fully reverse. So you already know how to deal with this kind of nature. So now you know how to deal with the different stress range. But even though in there is also the symmetric around this axis. This stress range is symmetric around x-axis. But now we are going to discuss about the alternative stress with the mean stress. The mean stress is the constant stress we can apply not instead this stress with this alternative stress. So what happened if we apply the constant stress on this alternative stress? This stress can be shifted to upward or downward. If it is a positive value, it will shift to upward. You can see in here. This is mean stress. So all the point in here shifted to upward. So if you apply the compressive load, it will go to downward. Okay. So we call this is mean stress. So you can see here. And this is the alternative stress you are going to apply. This is mean stress. So this is the amplitude of the sigma A. Later on, we will call sigma A for the label as a sigma A for the alternative stress, sigma M for the mean stress. Okay. So mean stress is we are going to apply if we are going to apply the constant load, constant stress on this element. Are we clear? Okay. So then, when we consider the pulley reverse technique, so you can see maximum and minimum stress are as a magnitude it is equal. The sign it will be changed, but as a magnitude it is equal. But in here, sigma maximum and sigma minimum will be changed. Sigma maximum means sigma M plus sigma A. You can see sigma minimum means sigma M minus sigma A. This is the range, alternative range. So we will consider this kind of nature now. So yeah, next slide. Definition of failure with the mean stress. It is usual consider component have failed if any part of it has exceed the yield point. Ordinarily, it may fail due to fatigue failure. So you know this explanation already. So if it is exceed yield point, it will fail. So obviously, one needs to define the degree of yielding which must occur before failure is said to have occurred. So this is the so what is the thing explained in here in this definition, you will understand very clearly in here. So even though you didn't understand the definition, so you can see this is alternative stress. With the y-axis, it is alternative stress. This is mean stress, sigma M. This sigma N and this sigma A. Okay. So sigma M, it is a constant in linear scale. This is also linear scale, but this is the alternative stress value. So if we apply only sigma M, that means constant load, what happened? This is just like a tensile load. This is tensile test. If you remember in your semester 1, you did tensile test. So this is like a tensile test. So you can see if you apply the increase the stress with the time, what happened? At the yield point, it will be yield. Then at the ultimate, reach the ultimate level, ultimate tensile strength level, then it will fail. So this is the simply, we can say this x-axis simply tensile test. Okay. So even though it's a compression, also same manner. And this is the alternative stress. So if we apply without, so this is in here you can see that one. So if sigma M is 0, that means there is no any mean stress, only alternative stress, pulley reverse technique. So then what happened? It will fail around endurance limit. So we already know that one. So it will fail at the endurance limit. if it is still 10 to the power 6 cycle strength value. But if we apply sigma A and sigma M together, so you can see here infinite, if it is below this sigma A, if it is below this value, it has an infinite fatigue lifetime. But if it is above, that's mean overstressing. It has a finite fatigue lifetime. It will break with some certain number of cycles. Okay. So that's why sigma A, if it is equals n infinite fatigue lifetime. Until this point, it has an infinite fatigue lifetime. And if sigma A equals 0, so I already explained that one. Okay. So it will no yield until this point. After there is a yield and the maximum point reached, it will break. And yeah, the fracture will be happen. But when you apply both these two together, sigma A and sigma M together, so you can't get this particular nature or this particular nature. So it is in between these two. So these three persons explain the three methods to analyze this thing. Gerber parabola. So you can, this is kind of overestimating. Okay. So you can see these dotted are actual data. So they already find out the materials with the sigma M, sigma A and sigma M apply together. They will find out the fracture point. So you can see with the Gerber's parabola, so many data inside. But even though it's failed, it is inside. So this is kind of overestimation. Okay. So we can't use this technique because with this technique, even though it's explained the material is safe, it is not safe. And the Schoenberg line. So he with his line, you can see so many lines above that point. So that means even though it is explained that particular material is not safe, it is safe because it will fail after that point. So Soderbergh also kind of very conservative. Okay. So Goodman line, that is the person who find out this technique, is a very good method. So you can see there is a, not, even though it is not homogeneous, I mean symmetrically distributed around that point, so it is fairly explain the failure mechanism. So if you use this curve for the failure analysis, this is a very good method, Goodman line technique. Okay. So it can, the data is scattered around this line, not perfectly symmetric, but close enough to the symmetry. So if you apply the stress sigma M and sigma A together, you need to use this line to predict the failure point. That means if we apply only tensile load, you can see after ultimate point it will break. And if you apply alternative stress only after endurance limit, if you apply above endurance limit value, so that particular material will be fail. But if you apply together those sigma A and sigma M, so assume this is the sigma M value, so you can draw the line. So if it is reached to this line, so that y coordinate explains the maximum sigma A you can apply. So you can't apply above that value, even though the endurance limit of this particular material has some value like Sn. You can't apply that much because we already apply sigma M also in here. So you can see here. So with this diagram, you can predict that particular material has an infinite fatigue lifetime or not. And you can find out the factor of safety as well. So with the so if you have the sigma M value and sigma A, so you can get the factor of safety, the ratio between these two. Okay. So if you have the operating stress values inside this triangle, you can see this line and these two axes, that material will be safe. But if it is above this line, it is not safe, it will be fail. and the inside this particular region, that particular material has infinite fatigue lifetime. If it is above, it is finite fatigue lifetime. It will fail with a certain number of cycles. So did you understand about the diagram? Any questions?
So typically we use the Goodman line
Hello?
because
I couldn't hear properly.
so we don't really use the Gerber or the Soderbergh line, right? Because
No,
the
we don't
Gerber's
we don't want to use. So just for the demonstration, we can explain these two, but Goodman line will be used in future for the calculations.
but the Soderbergh line,
Yeah.
isn't that the conservative estimate?
Sorry, I couldn't hear properly.
Like,
I don't know why.
yeah, the Soderbergh line,
Yeah.
isn't that more of a conservative estimate?
Even though it is a
Like,
conservative accept, this is the better way, which you can see when we do the calculation with the factor of safety and other things. This is the better way. We already proved it. Okay, so with this line, so all of the failures are above this line. That's why it is called conservative theory. But even though it is a conservative theory, so the practical manner they explain the Goodman is a better one. Okay.
okay, sir.
So don't worry about all the point above. So you can, if you use this particular method, definitely if you get some answers, it is very correct, because this is not fail with the any point. You can see any actual value, it is above. Are we clear?
Yes, sir.
Okay. So this is another diagram, the sigma maximum and sigma minimum, and mean stress and alternative stress. So 4 axes are there, you can see. So this is the, in this graph, okay, this is that graph, sigma m and sigma a, and this is sigma maximum and minimum and sigma maximum. So the particular material, okay, this is, they explain this is the material. So there's a two set of axes. Okay. This curve, particular curves give the lifetime, fatigue lifetime. Okay, so 4 times 10 to the power 4. This is 10 to the power 5 cycle. This is 10 to the power 6 cycle. So this particular line belong to certain lines. Okay. The curves are somewhere between Gerber and Goodman line. I told you in here, Goodman line, and so this is, even though we get as a symmetry, Goodman line around these points are symmetric around this Goodman line, even though I explained it is not totally perfect symmetry. So symmetric line will be in between Gerber and Goodman line. Okay, so that's why they mention here these lines in between Gerber and Goodman line. Okay, so that is a symmetrical. So if you have certain maximum stress value, you can draw the line. Okay, so if you draw the line, so you will get the minimum value, so 70, minimum 70, and this is the maximum minimum value. So crossing point is, okay, sorry, crossing point, you can get the number of cycles it will fail, or if you get the mean stress and alternative stress, you can get the number of cycle it will break. So I will discuss how to get the readings with the next few slides, I mean later. So don't worry about that. So you can use this particular diagram to get the number of cycle to break it. Okay, but in here you can't get the number of cycle to fail it. Okay, just you can say that particular element has an infinite lifetime or finite lifetime. So if it is above this Goodman line, you can say it has a finite fatigue lifetime. It will break at one point. But if it is inside your stress values, if it is inside this triangle, you can say it has a finite fatigue lifetime. That's only you can say in here. But using this diagram, you can say the number of cycle when it's if it is break, how many number of cycle you need to apply to break it or something like that. Okay. So later on, I will explain. Yeah, this is the very important thing. So stress with the stress razor. So we already introduced the KF with the last lecture. So you can use that KF as a strength reduction factor or stress increasing factor. That means that KF, when you find out the endurance limit, normally you will divide that SM prime and CS, CD, CL value, that calculation by KF. Okay, so that means it is strength reduction. But the KF, because strength will reduce because of stress is higher. Are we clear? Because around the stress tracer area, stress is very high. So because of this KF. So in the calculation, if you use KF with the stress, don't use again KF with the strength. That means if when you're going to find out the 10 to the power 6 cycle strength, don't divide by KF if you already introduce KF with the stress. So you will see with the calculation how we can, what I am going to tell now in here. So did you understand that? So if you introduce KF in here and here both place, it will cut off. That's why. Okay. Are we clear about that?
Yes, sir.
Okay. So that is the thing. Yes. With the notch, yeah, as I told you, there is no any unique method. Okay, you can apply for the stress or strength anyway, but for the KF or KT value in here, the question must be marked because it can be KT or KF. That's why. So the alternative stress, you can apply the KF value for the stress, but the mean value you don't want to use sometime, but you sometime they will use. It's depend on the situation. Okay, so there is, as they mentioned in here, there is no any favored technique for analyze this situation. Okay, so difference occur in how residual stress due to local yielding are handled. So yeah, that's the consideration of stress and strain in critical locations such as stress razor. So when you do the calculation, I already explained that one. So you need to consider the critical locations, stress razor or loading point. Yeah, that particular weak point you need to understand. There's much uncertainty as to what is actually happening within the material area. So when you do the calculation, yes. So there is a lack of knowledge between the calculations, this stress with the mean stress. So yeah, this is the technique you need to use as a stepwise. Both sigma and sigma m are increased by stress concentration factor. This is not the only method. So if you follow this method, it is very easy to do the calculation. That's why. So you don't want to use the KF at the strength when you're going to calculate the strength. So if you have you need to multiply sigma A, that means alternative stress and mean stress, using stress conservation factor, fatigue stress conservation factor. The appropriate K value is K even if we are considering limited life application. Any residual stress caused by the initial application of peak load can be determined from static stress strength curves. Yeah. So there is a different yield criterion. So like the nominal stress, if it is lower than yield strength, yeah, there is one condition. And sigma maximum, it is low if it is lower than or equal yield strength, and sigma maximum lower than or equal 1.1 yield strength. So different criterions are there. So normally in the questions they will provide the criterion if it is needed. So don't worry about that. Okay. So with this example, you will understand how we can do that what I am explaining here. Okay. So normally, even though in the theory you will be confused, but in the question you will easily understand how we can deal with that theory. So estimate the fatigue life of the following specimen manufactured from this is aluminium alloy solution heat treated and artificially aged with an ultimate tensile strength SU of 565 megapascal yield stress given subject to mean load sigma m, mean load 13.34 kilonewton, alternative load sigma A of amplitude 8.9 kilonewton. So they provide the load values. So you have the dimensions. You can see the width, the D value 76.2 millimeter, the stress laser diameter, B value 25.4, thickness, it is given. The loading directions, distributions. So how we can deal this kind of question? You need to find out the KF value first, and CS and CD and other things. So this there is axial load. That is the mean of mean load. So axial load. So you need to use these equations if you want anywhere to find out the nominal distress. At any point nominal distress you can find out using this equation. So around the stress trace area you need to multiply by K. So you need to find out this ratio and find out the KT value. So this is the axial load curve for the KT value. So there is only one curve. I already explained in the previous lecture. So KT value is 2.33 with the ratio of dB ratio. And then you need to find out the Q value, not sensitivity, because you need to find the KF. So ultimate resistance provided already. So this is the axial load. So you need to use these values. So if you find out the ultimate strength and notch radius in here, what is the notch radius? It is 25.4. In here, notch radius only be available until 4 millimeter. So in our case, it is 25. So we can't use this diagram for this calculation. Then what you need to do, there is another theory. So that theory you will learn from this question. So this is the theory. So as they mentioned, you don't want to remember this method. They will provide this graph, then you can easily find out. So they explain the KF value you can find out using this technique. So if you know ultimate tensile strength, and if you know the technique they will use, heat treated dough and then strength hardened, so you can find out the value for that square root A. So they call the neighbor constant. So you can, if you find the neighbor constant, you can substitute in here and find out the K. So that's the way they normally they will use. So it is, if it is 20 ultimate tensile strength, what is the value? I didn't remember. Yeah, they mentioned it. It is in KSI. You need to convert to KSI as well. So they provide in megapascal. You need to convert the KSI. So it is 82. So ultimate tensile strength 82, and you can find out the neighbor constants, this value, using this curve, draw the line and get the value. 82 somewhere here, and this 0.5 they they provide in inch. So you need to find out the 82 and 1.3 somewhere here. Okay, heat treated one. So then the material is heat treated. That's why for the aluminium alloy, it is aluminium ion. It is heat treated. In the question they mention in. So it is 0.13 inch. You need to convert to millimeter. So you can see in here they convert to millimeter. Then KF and relationship is provided. You can substitute here and find out the KF value. So don't worry about this technique. They will provide the equations and graph. So if you know any other requirements, you can easily find out, because in excess is ultimate strength, and the equation they will provide in your lecture note. The equation is provided, okay, with this KF and the relationship with the neighbor constant. So they substitute in here. So just calculate the KF value. No worries. Don't worry. Even though you can't use that particular technique what we used early, so you can use. So you need to prepare this kind of surprise. Okay, sometimes they will provide a different technique you need to use. Sometimes if they provide that kind of thing, you should have ability to grab that thing and do the calculation. So then nominal stress, as I told you in here, this is the equation. You don't want to keep it mind. So you can find out the stress using that equation. Substitute here. Then you will get the stress value. So loading is P, just put as a P. Then we know alternative stress. Then you can find out the maximum nominal stress, because we already find out the value for the nominal stress with the axial load. Then alternative stress we already know. So we need to get the sigma A and sigma M together. So you can multiply by this value. Okay. So the minimum value you can get for the from the difference between these two values, sigma M minus sigma M. So these are the maximum and minimum value without stress razor. So when we introduce stress razor, so we need to multiply by KF. We already find out the KF. So nominal stress, you need to multiply KF. When you're going to find out the maximum stress around the stress razor area, you need to multiply by KF. So you can multiply by KF, then you will get the minimum and maximum values. So both of these values below the yield stress, because yield stress 483. So it will not yield there. The maximum stress is in here 292.6. With this graph you can easily see that. So this is a loading curve. So you can see so stress around this point, it is very like this. Okay, it's a local area. Local area stress variation will be like this. So loading pattern like this in the local area. So maximum load is 8.9 plus 13.34, something like that. So that is maximum point load. This is minimum load. At the very beginning is 0. It will end up with the cycle with the minimum load. And stress will be vary. We already find out the stress without stress razor. These values, these two values. And the stress razor area, we are not going to change the loading pattern, same loading pattern, but stress will be vary because of this stress razor. This is stress razor. This is a one quadrant, first quadrant of the plate. Okay, this is the first quadrant of that particular hole. So you can see that edge of the that surface of the hole, around that area, there's a maximum stress. So you can see we already calculated that value as well in here. This is stress area, maximum minimum stresses. You can see. So you can calculate the fatigue lifetime using this curve I told you. With this example, I will explain. So the maximum value we already know now, but you can't use this diagram, this graph with the megapascal. You need to convert to KSI. So normally, if they will provide the relation between the megapascal and KSI, don't worry. Then you need to convert megapascal to KSI. Then find out the sigma maximum minimum around the stress phase area. That is the maximum value. Local area, the maximum value is very low. So you need to find out the maximum minimum value in the stress phase area in the KSI. Then use that coordinate. So this is 42.4, and this is the minimum value, 8.5. So draw the lines and the crossing point. So you can get the fatigue lifetime. You can see this line go through this point. So that is the fatigue lifetime. So in this particular loading pattern has that element has 4 times 10 to the power 5 cycle fatigue lifetime. So in this one, there's additional thing they did. They increase the same question. So same thing, just only change the mean load value and alternative load value. Earlier it was around 8 point something and 13 point something, but in here it is increased. It is increased until 24.47, and it is sigma A also increased until 20.03 kilonewton. So you can use same equation for the nominal stress. You don't want to again find out the KT and KF because same plate, same dimension. So this is the equation. So P only will be changed, the summation of these two and difference is between these two. So nominal maximum you can get from the get the summation, and this is the 10 to the power 3 belongs to kilonewton. Okay? It is 10 to the power 3, and this is the cross section of the. This is come up with the cross section. You will get the local area, that nominal stress maximum value. Local area minimum nominal stress will be give the difference between these two, sigma m and sigma m minus sigma A times that 6.2 10 to the power 3. This is in megapascal. So you will get the local area stresses, and then you can get the stress phase area maximum minimum values. You need to multiply by Kf. Kf will not change with the load, I mean applied load. So then you will get the stress maximum stress and minimum stress around the stress phase. You can see maximum stress, even though local area stress is lower than the yield strength, the maximum stress around the stress phase is higher than yield stress. So if we explain with the stress strain curve, you can see it is yield stress is it is 483. So we can't go beyond the 483 because even though it's a 584, it's try to yield, but in this particular element, yeah, it can't that particular. Okay, I will draw here. So this is the. So this is the point exceed the yield point, but it can't only move. The whole thing should be moved. So what happened? That stress will be saturated at that point because this one point, this point only can't change, move, it can't yield. So the whole cross section should be ready to yield. So in here, only this area reach to the reach above the stress. So what happened? It will be saturated. So with this slide, you can see. So the 584.7 and this value, difference between these two, the 44.49. Okay. So it will stay as a residual inside as a residual stress, and when we apply the compressive cycle, we are not with this diagram you can see. So we can't go beyond this range. So the load is same thing. Sorry. You can see in here that this is local area stress variation. This is the thing happen with the stress race area. You can see here, even though it should be reached to 584.7, can't go beyond 483. If it is going to 483, it will be yield. It will be permanently deformed. But this particular component can't be permanently deformed when reach this only this place reach to the maximum stress. So it should be this whole cross section should be reached to the maximum stress. Then it will be moved. So then what happened? It will be saturated, and when it's compressive load apply, that means with the alternative.
So what do you mean by saturate? Do you mean that
Saturate mean
force distributes, or
even though it should be reached to the 584, it will not go to the 584. It will remain as a 483. The stress around this point, it will remain as a 483. So there is a gap between these two. So it will come up with the compressive cycle. You can see. So even though it should be finished somewhere here, it will be finished somewhere here. Okay. The compressive load, it should be minus 43.2, but it will go below that point. You can see this is the difference between these two. Can you see? Did you got what I'm explaining?
yes? So what you're saying is it's not gonna yield. It's going, but with that extra force, it goes below the compressive.
Yeah, because
Below zero.
compressive side also we can go beyond until minus 483, isn't it? If it is a yield point. So, but the compressive side we are only reached to we can only reach to minus 43.2. So with the calculation, so sorry, at the minimum value 27.6. With this calculation, 58.5 minimum value. But there is a gap between these two. You can see the 40 between these two maximum value, the 44.49. So then so what you can do, the compressive side will be increased from this much. So you can get this summation. Okay.
Okay, sir.
So then it will be like this, because if it is also reached to 483, we can't apply to compressive cycle. We can't reach from this side until this point. What happened? The material to ready to apply that load to other side, compressive side. The tensile side, the positive side, we can't go beyond 483. The materials they absorb that stresses and release to the compressive cycle side. That's the way happen. The atoms will be ready to, the atom will be absorb that energy, because It can't go beyond this limit, this point only. You can see in here, whole regions are the blue and green color, but in this region only red color. So this point only can't move. So for an example, okay, assume there is a hole. So holes filled with the student. Okay, the door also closed, but only one student in the middle somewhere. One student want to. He got so angry, he want to go outside. Okay, but he can't go outside because others don't want to go outside. Others need to give the space to go outside to him, because whole room filled with the students, no space to move. Okay, something like that. If the row of the student, one row of the student, if it is moved, then that particular student can move, isn't it? Are we clear?
Yes, sir.
So something like that. One particular point, on if it is reached to the yield point, it will not move. But the whole cross section should be reached to the yield stress. So that is the thing you should understand in here. So that stress will go to the other side. Okay. Assume there is two doors in that room. The one door is closed, the main door is closed, but other door is open. Then that particular student push to that main door, towards to that main door, but that particular student don't want to move. Then what happened? The reaction will be come onto that particular stress student. That means that angry student. Then that whole the line behind that angry student will be moved to that second door, towards that second door. Are we clear?
Yes, sir.
So something like that. Okay, just for understanding, I explained that sometimes you can't apply everything into that classroom. Okay, because just for understanding only, don't use to understand everything, each and everything with this stress cycle with the classroom. We can't demonstrate everything, but for an understand, you will easily get that thing. I think yes, quite enough. Are we clear? So with the next cycle, you can see. So it will reach to the 483. The second cycle, load is same thing. Load will not change, same pattern. What happened? The maximum stress 483, because that is that particular door also close someone, then it can't move. So then that person will be remain as the same point, same place. Okay. So what happened? You can see in here to here the difference between these 2 points, 500, the y direction is different, 584. You can see here to here also 584.7 is available. If you get the difference between these two, you can see. Okay. In between these two difference is 584.7. So maximum stress is there now. Minimum stress also there. Are we clear? Any questions? From second cycle to third cycle, fourth cycle, same pattern, same way. But at the first cycle, this point only reached the maximum yield stress, so it will balance like this way. I hope it's clear. I will move to the slide. Okay.
Excuse me, sir.
Yeah.
So after 400, after the stress passing 483, does it compress as a reaction of the other atoms?
Something like that, inside the microstructural thing, that thing. So it's not actual mechanical thing. So it is a microstructural happen. Okay, it will absorb inside the atom. It will release as a compressive load.
Okay, sir.
Are we clear?
Yeah.
So it is actually it's a part of kinetic, of molecular kinetic, atomic kinetic. So different subjective thing. Okay, so don't worry about too much about that thing. Just understand what happened in roughly, at least understand what happened with the only one point of the whole component reached to yield point. What happened to that stress variations? That's all you need to understand. Is it clear?
Yes, sir.
Okay. So then you already find out the maximum stress and minimum stress now. So you can use the same diagram to convert the maximum minimum stresses to KSI value. So those are the KSI value. So then draw the line. You can see the crossing point. Through the crossing point, there is a line go through. So you go through, then so then you can get the lifetime 10 to the power 4 cycle. So earlier it was a 4 times, no, I didn't remember the value. So I think 4 times 10 to the 5 cycle. So now it's reduced to 10 to the power 4 cycles, because when we increase the magnitude of the alternative stress and mean stress, number of cycle to break that particular specimen will be reduced. Yeah. So then same example, in here you can see same example, only per cycle, first loading cycle, they apply the 44.5 kilonewton mean load. From second cycle, they apply same load at the first part we explained 13.34 kilonewton, and alternative load throughout the this procedure 8.9 kilonewton. So at the first cycle, mean load only applies a 44.5 kilonewton. So we need to find out we don't want to find out the second cycle stress, because we already find out, isn't it? The first part of this example, we already find out the maximum stress around the stress tracer with this mean load and alternative load. So we need to find out the maximum stress and minimum stress around the stress tracer area and local area with the first cycle, so with the mean load. So what you need to do, you need to find out the maximum load and minimum load. So this is very easy to calculate, because if it is 44.4, so very easy to calculate, because 44.4 means at the 44.4 it is reached to the maximum at the stress tracer area, it is reached to the yield point. Okay, so in here they didn't calculate each and everything. So what they did, so they find out the local area stress and reduce that the difference between the yield point and maximum value. Okay, they will get the maximum minimum local area stresses. Then as I told you, so they get from these value from the first example. Okay, so I'm not going to do the calculation. I will show you what happened then. Okay? So you can do the calculation from first step and get the values. You will get the same value like in here. So this is the first cycle. Okay, this is very interesting. You can see. So this is the first cycle. This is second cycle. See, in second cycle, we will use the same method. We will use the part A. If you consider this is part C, earlier one is a part B. So this is in part A. We will use this loading cycle. But in the first cycle only, we will use the different pattern. So what happened? Local area stress variation. It is normally we can calculate. This is a part B loading pattern. This is part A loading pattern. Okay. And what happened, the stress raise area, you can see in here, it can't reach to the 584.7, will remain as a 483 local area. And so this the stress raise area, then it will compress more and more. And since second cycle, it has a stress like this. So in the part A, I will go to the part A now. So I didn't remember the values. The part A, yeah, you can see the maximum value. Stress local area, stress raise area, it is 292.6. But you can see in here, maximum stress 190.9. And minimum stress is lower than earlier, part A. Part A is, it was some different value. But you can see with this loading pattern, what you can understand, if you apply free load, that means preload, before you are going to apply some kind of load pattern, you can preload this particular element. It kind of warm up. Okay, so before you are doing some kind of sport, practicing or something, even though you are going to gym, before you are going to do some exercises, you will do this warm up session. So this is kind of warm up. So with this first cycle, this particular material will be warm up. And then, even though you apply this, in the part A, you will apply this load pattern. You will reach the maximum stress. It is around 292. But in here, with this preload, the maximum stress it can reach 190. So that means that particular atoms inside this element, those are ready to move without any trouble. So stress is not accumulate too much. So this is kind of warm up. Okay. So you can use this kind of technique when you use some machine element. You can preload it and remove that load, and you can apply the required loading pattern. So did you understand what I'm explaining here?
Yes, sir.
Okay. So you can find out the lifetime. With the lifetime, yeah.
So what is the advantage when we giving the
Preload.
In the machine?
Because you can increase the lifetime. You can see in here, component lifetime you can increase. You can see in here the maximum stress in the KSI, minimum stress in local, stress raise area is in KSI. You can draw the line and you can see your lifetime of the component, it is about 10 to the power 9 cycles. If you apply this load without preloading, only one cycle we use, okay, one cycle preloading, but without that preloading, same stress pattern, you will get the lifetime 4 times 10 to the power 5 cycle. So as I got some example, like when you're going to gym, if you go to gym, you know gym more. If you do some sport, you will warm up. What is the importance of warm up? You will not get the cramp or crack of bone, something like that, because your body ready to move. Okay, with the warm up, so that your failure is lower, cramp is lower. But the same way, the material also, if it is warm up, the preload, the materials lifetime also will be increased. Without warm up, if you do some sport, you can't do that sport too much time. I mean, you will be tired very easily. Am I right? Did you understand I don't know who the person asked the question. Hello?
I'm Virant. I'm Virant.
Okay, did you understand?
Yes.
So the import and what are the benefits? You asked what is the import. So what is the usage of this one? Usage is you can apply this one for the element, the component. If it is a shaft, to increase the lifetime of the shaft with the loading pattern. So you can see in here, same loading pattern without preload, it is 4 times 10 to the 5 cycle. But if you apply preload, only one cycle preload, the which higher load with higher load, so material will be warm up, then lifetime will be increased. It is higher than 10 to the power 9 cycle because it will not this line not going through this crossing point. It is below that one as well. So it is above. That's why it is above. That means 10 to the power 10 cycle or something like that. Are we clear?
Sir, is there such a thing as a optimal preload? Because say for instance in this example, they,
in here it's, you can't go beyond the yield stress.
yes, but in this example they went beyond the yield stress.
No,
And
even though they apply the even though they apply the beyond the yield stress, so it will remain as a yield strength because you need to apply some stress above the yield stress, then only it will be preload.
yeah, yes, sir. That's what I'm saying. Say for instance, you applied yields above the yield stress. Would there be a circumstance where the stress was too great and it just
Can't
fractured
apply.
without?
Okay, in here the yield strength it is 483, so you can't go beyond something. So you need to calculate the stress load value. You need to apply the local area yield point stress. Did you get what I'm explaining? So you can calculate.
So in this example, would the local area yield point stress be 483?
Yeah, local area stress, if it is reached to 483, you can't preload above that level. So in here you
But,
can see,
sir,
yeah,
in this example, isn't the preload 584? I know it doesn't exceed 483, but the preload is 584, isn't it?
yeah, but it is local. This is not a local area. This is a yield point. That is a stress race area. The same with the same load value, the local area stress it is around 275. Okay, so you can preload. You asking what is the preload, the maximum value, isn't it? So maximum
Yes,
value, it is if you reach this the local area stress value here, that is the maximum value, maximum load. You can calculate it. So if you want to find out the maximum load value, what you need to do, you can substitute the stress as a 483 in this equation. I will show you. In this equation, you can apply the maximum nominal stress, this one, as a 483 and divide by this value, you will get the load value. Okay, that is the maximum load you can apply as a preload. Are we clear? So you can't apply beyond that preload because then the whole cross section ready to yield. That's why. So whole cross section ready to yield. Are we clear? Yeah.
Slide.
I couldn't hear.
So the whole cross section can't exceed 483.
Yeah.
But the stress raise it does exceed.
Yes, stress raises can exceed because that area can't move alone, because if this point should move, if it is want to move, it should move together this cross section, no? That the particular point movement means it will be plastically deformed. If it is plastically deformed, that whole cross sectional atom should be ready to move.
And because of the stress razor exceeding, it leads to residual stress and a longer life.
Yeah.
Okay.
Are we clear? So do the mind exercises, then you will understand what I'm explaining. Okay. So at the very first time you heard this one, you will not understand sometime. You just try to understand. If you have any question, you can ask next time. Okay. Do the do the tutorial and do the exercises in here, and try to understand and read the I already given some reference as well. No? So read that one, and so then you will grab some idea, and you will understand what I'm explaining. If you still you don't understand, you can ask next time. Is it okay? Yeah.
Okay. Okay, sir.
Okay. So I will move. So then with the preload, we can increase the lifetime of the particular element. So keep it in mind in your mind. Then the part D. In the part D, you can see they will use mean load as the uh, part B. We will use same load, no? Isn't it? I didn't remember the values. Part B. No, it is different. Okay, so this is a much higher mean load value. In here, you can see the 40.03, and alternative load. It is also much higher value. So this is a different condition now. So we can use same equations, calculate the nominal stress, local area nominal maximum stress, and local area nominal minimum stress. You can calculate, and you will get the value. You can see local area also reach to the very close to the yield point. You can see in here, in the local area, if it is reached to the 483, it will be yield very quickly. So you can find out the stress razor area is maximum and minimum stresses using KF value. So multiply those stresses by KF. So you can see this is very high stress. So let's see, this is loading pattern. So local area stresses. You can see it is also reached to the very near to the yield point now. This is the yield point. Okay, this is the stress razor area, stress variation. You can see. Okay. So let's see what happened the number of cycles to fail. You can see if we use this kind of stress pattern, you can see after converting the KSI, so the maximum stress 70 and minimum stress is minus 44. So 70, this is minus 74 somewhere here. Okay, so you will get it is below 10 to the power 3 cycle. Okay. So lifetime is very low. If you use very high stress loading pattern, very high values, you have low number of cycle to fail. So did you understand all of these things with this four? There is a, if you categorize A, B, C, D. So with the part A and B and C and D, so you can easily understand what happened with the stress variation. What is the variation of the fatigue lifetime? So do these exercises at home. So don't only read, okay? So don't read the lecture note. Read it and try yourself as well. Don't only read and okay, you think okay, I understood something like that, but do the calculation and justify it. Okay. So that's all about the lecture number 5. So I will go to the tutorial. Can you tell me, do you have this tutorial with you? Tihan, at least someone. This one or this one? I don't know. Okay, I will use
Give
this
me
one.
1 second, sir.
Okay.
We have that one, sir. The
Okay.
one that you're using now.
This one, no? Yeah. Okay, so you can see in this diagram. So the tutorial 2 to
No, not this one. The other one. Sorry,
this one.
I got confused.
This one. This one, no?
That's the one.
Okay. Okay. So normally same dimensions we already use in the tutorial 2, 3. Then this is 4. So tutorial number 5 also we will use same diagram. Okay. So but only change little change with this little change, the calculations also will be vary. Okay. So in the exam you need to be careful. So what are the loading pattern available in here? What are the stress ratios are available in here? Something like that. Okay. So I will read the question and I will explain. But before that, I need to ask: did you try out this question? Because you already followed the lecture, I think. So did you have any difficulties to do the calculations? Because I think you already try to listen the lecture already. So I thought you already try to do some calculations. Some questions. Did you try out, Tihan? I'm not asking for only Tihan. Okay, others also. Is Shena is there? Shena?
Yes, sir.
Shena, did you try out these questions?
Not this answer. The
Okay.
first question, the bottom.
Sorry.
The question with the flat plates.
Okay. So so if someone did the questions, you can ask the where you are struggle. Okay, you are where you stuck, something like that. So if you stuck somewhere when you do the calculation, even though you have answer with you, so if you don't understand why we do this one, what is the reason for this one or something like that, you can ask now. Okay, so that's why I'm asking, did you try out the questions? So don't only listen to me, just try out to get the I mean, I will read this one and I will explain how to do this one. Rather than explain that one, you should get the benefit. So with asking some questions, okay, so if you don't have any question, it's better. But if you have anything to ask, any doubt, you should ask in here. For that, you should try out this question. That's why I'm asking. Okay, so next time, at least I told you last time also, try out the questions. So you have lectures, so you can follow that one as well, and try out the questions during this time. So even though in this lecture time also, you can ask any questions. So if you follow the lecture, it doesn't matter. You can listen, and when you listen that I lecture and when I explain something, if it is different or something like that, you can ask. Okay. Sometimes both of us telling same thing, the same different manner. Sometimes that's right. Okay.
Excuse me, sir.
Yeah.
So this beam has three stress concentrations. So we have to take three values for Sn, right?
Sorry, I couldn't hear last thing. Last what I said. Last sentence. What you said.
This beam has three stress concentrations. So
Yeah,
we have to,
with the 2 pillar 10, 1 group. Yeah.
yeah, we have to take three values for Sn, right?
Yes. Not 3,
So
4 value with the loading point.
yeah.
Yeah.
So
Yeah.
so for plotting the Sn curve to determine the life of the component, what we should use, is it the least Sn value?
Yeah. Least. We need to consider least SN I mean least strength value, which curve gives the least endurance limit.
Okay.
Okay, so that's good. So when you do these calculations, okay, still there is someone admitting. Okay, I don't know why. So in this question, you can see. So I'm not going to read these questions. There is a 2 pillar and 1 row. You can see the pillar dimensions are different. What are the dimensions? 0.5 millimeter, 1 millimeter, and a BHN value provided. So you can find out the SU value. The important thing, the rotate at high speed while imposed load vary according to the loading sequence table 1, which repeat independently. Calculate the component life in the number of cycle. So you can see the number of cycle with this load. So what you need to do, the very first thing you need to calculate the KF value, KF and KF dash. Okay. So for that you need to find out the CS, CD, CL, or everything. So there is a method you can find out the, rather than using strength, you can use the load value. Okay, 10 to the power 3 load value, because construct the FN plot or SN plot is doesn't matter. Okay, but better you use the FN plot, because strength vary with the cross section, but load is not vary with the cross section. So you can see what is the difference between these two in later. I will explain what is the difference between these two, load and stress. So if you already know, it's okay. So you can calculate the component. So this is method 1, and method 2, you can plot the SN curve. Okay. So calculate the 10 to the power 6 cycle and endurance limit and 10 to the power 3 cycle strength. From that you can find out the load value for those relevant point and FN plot, and then calculate the component lifetime. Or you can use SN curve, but this is not suitable for everywhere. In this question we can use sometime, but this is very good way. Okay, keep it in mind. So anyway, we need to calculate these things. So I'm not going to explain how we can. Yeah.
So quick question for the TUTE. Will the exam style questions be similar to this, the format? Because for the TUTE question,
Yeah.
first you find K, then you find the SN value, and then you find the allowable, F allowable for each of those grooves. Sorry,
Yeah.
each of the fillets, and then one for the groove, and then you compare all of those, and based off that, you figure which one will have the failure point.
Yeah. Yeah. You can use. The thing is, you should do some exercises. Then you will understand which one is very good for this kind of question. Okay, so the exam always they will not use same method. Sometimes depend on the question. So the question what you saw in the exam past paper somewhere else, so that questions doing some particular method, that's right, but it's depend on the question. Sometimes you need to use the strength values, sometimes you need to use the force value, but I mentioned the better way if you use the force values, I mean load. Okay, because it is not vary with the cross section, that's why. So so you will understand next lecture, next week, when I explain the lecture material, you will understand what why I am telling these things. Okay. So I think I don't want to explain how to find out the CL and CD and CS. Is it clear? No? Is it clear? Do I want to explain? Because it is rotating bending condition, so you can read this table.
No, sir, that's clear. We did this last time.
Okay, so I don't want to explain this, how to find out the CS and CL and the pilot KT value. So you need to consider each pilot separately, find out the KT values. Okay, So select the proper graph. I already explained this thing as well. So you can use same graph for the both pilot, but you will get the separate values, okay, because the radius of the pilot will be changed. So you can see this ratio is same, but this ratio is different. So KT value you can get, then you can find out the Q value for both pillar, okay. So using this graph, so you know how to use this graph as well. And then you can find out the K for both pillar. So you already know KT, you know Q, you know CS value. So you substitute here, you can find out the both pillar KT values. And then what you can do, find out the strength at the 10⁶ cycle. That is endurance limit for still. So you already have those values. You can substitute K value for 10⁶ cycle. For both pillar, you can find out the only changing in the both pillar in the KF value. The denominator is same, but this value will only change. So you can find out the endurance limit for the both pillar. So you need to find out the both pillar 10⁶ cycle strength. For that you need to use this graph. I already explained this how to use this graph. So you know the ultimate resistance strength. You can get this ratio. If you know the KF value, you can. If you know this ratio, you can find out the KF prime. So then, yeah, this is the ratio. Then you can find out the KF prime for both pillar. Okay. Because the K prime, then you can use that K prime value to find out the 10⁶ cycle strength. So use this equation, find out the both pillar 10⁶ cycle strength. Then you can use the equations, this equation available at the graph. So use that equation. So you can find out the stress using that equations, bending moment. So I'm not going to explain how to find out the bending moment, as you already know how to do how to get the bending moment at this 0.5 millimeter radius pillar at that point, bending moment, and use the dimensions and find out the stress with the load value, F load value, and this stress, if it is equal to the 10⁶ cycle strength value, this load value is, we can call the fracture point load, that is endurance limit load value. So this is the endurance point load value. You can see they used also load values to plot in the FN curve. So 10⁶ cycle 0.5 pillar, same equation. This equation not change, but load value will, so that is strength will be changed. So in here this is strength. So you can use and you can find out the load value for the 10⁶ cycle. So same manner, 1 millimeter fillet also you can calculate the load value for fracture point and the 10⁶ cycle. So that means endurance limit and 10⁶ cycle load value. Then similar way you can use to these calculations for the groove. At the groove you can find out the KT this way. This is the equation, you don't remember. Then you can find out the Q value of sensitivity, then KF and KF dash. KF dash you don't want to again find out the ratio because same ratio. If it is ultimate size is same, so ratio is same. So you can find out the KF dash value. Then you need to find out 10⁶ cycle strength and 10⁶ cycle strength using these three at the group. Then you need to use that particular equation, calculate the same way the 10⁶ cycle load value, 10⁶ cycle load value, compare those loading load values as each point. Okay, and same time you need to do the loading point, calculate the loading point strength. So this is the calculation. Kf is equal 1 in here. So we can calculate 10⁶ cycle strength value at the loading point. So these are the strength values. Then you can find out the load value at that point, like this. These are loading point, endurance limit, strength, loading value, and loading point, load value at the 10⁻³ cycle. Then compare those values. So if you want, you can plot, or you can with the value. If they ask to plot this curve, you need to plot this curve. Otherwise, you can just compare the values. So you can see this is the blue color one, 0.5 pilot, and the red and brown color is that are 1 millimeter, that 1 millimeter pilot one, and the loading point, this is purple one. The green one, so groove one is minimum loading value for the endurance limit. So that means the groove is the we need to consider the groove, that is the least value. So you can get the equation for the Fn curve, that relation between the Fn Fn between the 10⁻³ and 10⁻⁶ cycle linear region equation you can get for the groove. You don't want to consider other three curves. So use that equations and substitute at the groove values for the 10⁻³ cycle and 10⁻⁶ cycle loading value. Find out the A and B. So then you need to use that tables. They provide the initial table. If you remember, these are the loading magnitude of the load. Then number of cycles they already provide. So you need to find out the, that capital component lifetime with this load. Substitute here load value and find out the number of cycles or component lifetime with this load. But with this calculation, you can see in here the loading point. So 10 to the power 3 SN value, it is 13.06. It was at the groove. What is the value? This 8.67. Okay, 8.67. This is 13.06. So this 8 value at the groove 10⁻⁶ cycle loading value endurance limit, it is 8 point something. So it is this 8 value, 8 is lower than 8 point value. So this is not affect to the component life. So that's why it is infinite. So above 8.3 or something, there was some value. So above that value, it will affect to the component lifetime. So you can calculate this equation valid for above 8.36 that value. So you can use those value to calculate the capital N, then get the ratio between these two and get the summation. Then a component lifetime you can calculate using this equation, because total number of cycle you have now is 115. They didn't mention the time duration for this okay, this loading pattern. They will not apply within 1 hour, within 20 seconds or something like that earlier. But you know, they asked the question answer with the number of cycles. They didn't answer hour or the per second, second in the second, no, in per hour, in day. They didn't ask. So what you can do with this number of cycles, this is the damage. So you can find out the to reach to this value reach to 1, what is the number of cycles? So this is 100. If it is 115, so this is the damage. So if damage is 1, so if you multiply by 1 this one, this is the total number of cycles to break the sample. That is the component lifetime. So this is the number of cycles after doing this calculation. Are we clear? Any questions? Yeah.
No, sir, that's okay.
Okay. Then yeah. So in here they use the SN curve as well. Okay, how to deal with that one? Okay, the same manner. With the stress, you can calculate the different way. You will get the you can calculate the, you can see in here the stress. You need to calculate the number of cycle for the each stress. Are we clear? The fillet number 1, you need to calculate the number of cycle. Fillet number 2, that means you need to calculate the number of cycle. Okay, and the groove, you need to calculate the number of cycle. The loading point, you need to calculate the number of cycle. Then you need to consider the number of cycles. The lower number of cycle is the answer. Are we clear? You will get the same answer. So that this is difficult. The second method is difficult. So you need to calculate this kind of table for each weakest point. Are we clear? So you will get the same answer. So this is 1.741 10 to the power 5 cycle. In here, you will get the answer. So see, it was a 1.741 earlier. So 7.3, so 1.743. It was 1 in here with the FN curve. So are we clear, Tihan? So with the, if you use stress or strength, you need to calculate the number of cycle to fail for each point. Tihan?
Yes, sir.
Yeah. So so don't use this method. Do the calculation at the exam. This is very lengthy. You can see. This is very lengthy. You need to find out this. Yeah.
So can't you take the minimum SN values?
No, don't do that. Because SN curve, if you use SN curve, what happened? The SN curves, you can plot and you can see some of the curves going to least value and some of curves reach to least value with the low number of size. Okay, assume some curve like this. I will draw in here. Then you can see. Yeah. So assume this is one curve. There is another curve. It will reach lower. Assume this is S. Okay, SN. So this is reach around 5 times 10 to the power 6 cycle. This is log, no? Okay, this is 5. I see. This is 3.5. So even though this is least SN value, this is reached with the lower number of cycles. This is reached to the induced training, isn't it? Are we clear what I'm explaining? So this is not good. So you will get this kind of curves if you plot. So you are in trouble there. So you don't know which one you need to select. This will reach this number with this number of cycle least SN. Are we clear? So don't use SN curve, the one single SN equation. That means SN equation like this. This equation you can use for each and every point. Even though you derive this equation for the groove, it doesn't matter because you use this equation for the load. So load not change with the point. Stress will be changed. That's why we call it stress raiser. Those area is stress raising area, not load raising area. So, but if you use SN equation, you can see here they calculate SN equation for each and every point and find out the number of cycle for each point for the component lifetime. They will calculate with the number of cycle, and they check which one is least one. Then that least one is the answer. Are we clear?
Yes, sir.
Okay. The question number 3. Question number 2. So I'm not going to explain this question, so you can do that one. Okay. So there is a same type of question. Only difference in here, they didn't. This is unknown. This number of this magnitude. This is stress. They are going to apply X number of cycles. You need to find out this X value. They provide us the component lifetime. So earlier we find out this value, component lifetime. Now we have this value. We need to find out the X. So you can deal with that question. Okay, I'm not going to explain that one. Answer is 79. They mention in here. So I hope you can do that one. Okay. So same calculation. There is one thing in this. Okay, I will explain that one little bit with this table. In here, the assume that 10 is X. So you will get the some value X divided by this value. Okay. So when you get the summation, there is X, and there is also X. So you have the N value. This value you have already. So this is available with the X. So you can subject X and get this value. That's all. Are we clear? Yeah. No, someone else.
Yeah, that's okay. That's just working back.
Okay. Shanal, do you have any difficulty when you do some calculation in here?
So I tried to go with the SN method.
Okay.
Yeah.
So better you can use FN curve. Okay.
Yeah.
So I hope you understand what is the reason for that I'm telling. So if they ask at the exam, you need to use SN curve, you should do that. Okay. Don't use FN curve then. But if they didn't mention the method, like you can use either FN curve or SN curve, doesn't matter. But from out of these two, better one is FN curve.
So it is because of the SN. The
You need to
strength is
calculate the SN equation for each point. That's why. And
yeah, because
the
the
table calculation also you need to do the each point. It is type based enough. Is it clear?
yes, sir. Yeah.
So in this question, they provide the load and number of cycles, and two different loading sequence they provide. So you need to calculate the number of cycles, I think. So in the first part, if the component is subject to the loading sequence shown in table 3, which repeat independently, calculate the component life in the number of cycles. Same thing you need to calculate for the table 4. So when you do, you need to calculate. I will just explain how to do it. I'm not going to do in the detail wise. I'm not going to explain. So you need to find out the KF value in here and KF value in here, and there is no any KF value, but you need to find out the strength in here. So you can find out CDC here, CS and Q value, KF and KF prime. So in here, okay, sometime in here. Yeah. So do you have the answer for these questions in here? I don't know if you have this one. Yeah.
Yes, sir. We have the answer.
Okay. So in my case, in this cute, I don't have the answer for that one. Okay. Anyway, so you can find out the CS, CD, CL, and find out the KT value. And then K prime, and then each stress ratio point, the strength 10 to the power 6 cycle and 10 to the power 3 cycle. Okay. And then find out the using that equation, you can find out the equations for the F. Then you can get the value for the endurance limit load value using each 10 to the power 6 cycles value for the each point. If you want to the above, this 10 to the power 6 cycle strength value, you can this is 10 to the power 6 cycle to a 4 millimeter hole, so 2 millimeter hole, and 10 to the power 3 cycle 4 millimeter hole strength is in here. So you can calculate the 10 to the power 3 cycle load value likewise. And mid-span means loading point. You can calculate the loading point. So in the load will applied in the mid-span. So you can calculate the 10 to the power 6 cycle loading value, 10 to the power 3 cycle loading value. Then you can plot what, or you can see the in here also 4 millimeter one is the critical one. So you can consider the 4 millimeter hole values for the derive the equation. So derive the equations and define the A and B like this, and then yeah, in here I think they mainly consider mid-span and yeah, okay, I'm sorry. So mid-span lower point is 10 to the power 3. When we consider 10 to the power 3 strength, they will consider mid-span. Okay, 10 to the power 6 cycle, when we consider, they will consider the 4 millimeter hole, because it is floating, and the data point you can see mid-span has a lower value for 10 to the power 3 cycle. Okay, so they define two equation for the two 10 to the power 3 and 10 to the power 6 values. So two equation. So we will use both equations to calculate that. Okay, you can see in here different equation, in here different equation, and you can see the 4 millimeter one, 4 millimeter hole. They use this loading pattern and number of cycles, and you can see the yield point load value, and according to that you can consider the what is the infinite fatigue lifetime, what is the not infinite values. So then get the ratios and get the number of cycles, and so you need to same time you need to do the mid-span as well, and get the component level. According to these two values, you need to consider the least value. Okay, because in here mid-span is lowest, in here 4 millimeter hole is lowest. So we don't know which one we need to consider. So you need to do the calculation for both. If you have cosine line like this, earlier we don't have that problem, because all the line was like this and other line was the lower, the shifted to downward. But in here the cosine each other. So at that time you need to consider both of line. Do the calculation for both and find out the number of cycle respectively both of line using the both of line equations, and least value is the answer. So are we clear? So same thing you can do the part B. So only different in the loading pattern. Other thing same, but in 4 millimeter and mid-span again we will consider. Do the calculation, least value will be at the mid-span. In here also mid-span. Yeah, it is also mid-span. So are we clear? Any questions, Sena? So I thought, I think you did with the strength, no?
Yes, sir.
So if you are going to do this calculation with the strength, what you need to do, you need to define the 4 millimeter diameter hole SN equation, 2 millimeter diameter hole SN equation, midi-span SN equation, and define the 3 tables, and find out the component lifetime, and least value will be the answer.
Yes, sir.
It's not a wrong thing, but it will spend more time rather than FN curve.
Yeah.
Are we clear?
Yes, sir.
So any questions from others of Shenal? So can we conclude now? And can we wrap session? Is it okay? Kian or Shenal or someone? So how many students available in here now? Only 5 students, okay? So don't you have any questions? Can I stop?
Yeah, okay, sir.
Okay, thank you. I will see you in next lecture, lecture number 6 and tutorial number 5. But better if you go through the lecture note and tutorial, that's better. Otherwise, no point to do this kind of lecture, okay? Because so you have all the facilities. You can go through the lecture. You have the answers and questions both. So do the questions. Otherwise, you are in suffer at the exam, okay? So so I can't help then after the exam. So I can only help before the exam. So better you can do the questions and try out, and if you have any question you can ask. So in here also attendance very poor, okay? The 5 students here. So that's not good. I will upload this lecture, but I don't know. So if you have any question, you can ask now itself. But otherwise, if you are going to watch this video and you can ask later, this question is not practical, I think. Okay,
Excuse me,
then. Yeah.
so in page 18, the tutorial solution in this part,
Yeah.
page 18, the 6 m mean the momentum, right?
Sorry, this M. This one, no? I couldn't hear you. This one?
Yeah, m mean moment.
Bending moment.
Yeah, okay. That's why I take the capital F over 2. No? Capital F over 2 into 30.
30.
Yeah.
Yeah. Capital F over 2 means this is the reaction at the supporting point. So this is the distance. I think the length of the plate is 60. I think. I don't know. 60 or the length between, yeah, in here the load, if it is F, this is a reaction. If it is a midi span, this is F upon 2, this is the length, this is the bending moment.
Okay.
Right?
Good.
Okay, so then I will stop if you don't have any other questions. Okay, thank you.
Thank you, sir.